Okay, so now we're going to talk about the kinetics of radioactive decay. And the very first thing I want to say here is that all radioactive decay are first order processes. All right, so there's no such thing as a second order or zero order decay. All decay processes are first order processes. So that's the first thing you need to keep in mind. So if you have a nucleus and it decays to form other particles, which are oftentimes referred to as daughter particles, then the rate of the reaction, which can be measured as the rate of decrease of the number of particles over time, that rate will be equal to a constant lambda times the actual number of particles that is present at that time, represented by the uppercase n here, and that is oftentimes referred to or equal to what is known as the activity of the nuclei. Now, the activity is actually measured using an instrument known as a Geiger counter, which I'm going to talk about shortly. So basically, when we talk about the activity of some nuclear material, we're talking about the rate at which it decays. So if we set this equation equals to lambda n, and lambda, by the way, is known as the decay constant, then we can rearrange this to get this expression. The number of particles at a particular time is equal to the initial number of particles times e raised to the minus lambda t. All right. Another way of expressing it is shown here, right? The natural log of n at the time t equals to the natural log of the initial amount of particles n0 minus lambda t, right? So n represents the number of times or number of atoms at time t, and lambda, as I said before, is called the decay constant, which is similar to the rate constant when it comes to first order chemical reactions. And as a result, we can write down this equation, which represents the half-life of the decay process. The half-life is equal to ln2 divided by k, or lambda, I should say. So the half-life here is basically meaning the same thing as the half-life we discussed in first-order kinetics chemical reactions, where it is the time taken for half the amount of material to decay. All right. So this is basically it as far as the equations for the decay, kinetics of decay of nuclear material. All right. So if you plot the number of particles versus time, this is what you're going to get, a smooth curve. If you plot the natural log of the number of particles versus time, you're going to get a straight line. And of course, these shapes come about as a result of these equations right here. In this particular case, the slope is negative, and it will give you the value of the decay constant. All right. The intercept on the y-axis will give this value here, the natural log of the initial amount of particles. All right. So this is the instrument I was referring to, the Geiger counter. Basically, it consists of this tube which has a window which allows radioactive radiation to pass through. So what you do is point this at your radioactive material, and it produces radioactive radiation, which ionizes the argon gas inside here. And basically, when the argon gas is ionized, it will basically cause a current to flow through the external circuit, because the positive ions will move to the cathode and negative ions will move to the anode, and therefore you're going to get an external circuit. So each time a particle is ionized, it is registered on the counter right here, and that is proportional. Whatever you register here will be proportional to the number of particles that was produced by the nuclear material. All right, so that's a very brief description as to how the Geiger counter works. Okay, now let's talk about radiocarbon dating. This is basically a method that is used to determine the age of artifacts and so on. And basically it's based on this reaction right here. Well, actually two reactions. The first of which is the reaction between the nitrogen-14 nucleus and the neutron to form carbon-14, and then the carbon-14 itself reacts to form back the nitrogen-14 nucleus. All right. Now, as a result of these two reactions, as stated here, the carbon-14 level on Earth remains constant, right? and that results in carbon-14 incorporated into the atmospheric CO2, which would be absorbed by living organisms, including plants, right? In fact, CO2 is absorbed by the plants, of course, via the process of photosynthesis, and the animals consume these plants, right? So in a living organism, the level of carbon-14 basically remains the same as a result of the carbon dioxide being absorbed into these living tissues, and then the carbon-14 from the carbon dioxide decaying. So therefore the level of carbon-14 remains the same, constant, while the being or organism is alive. When the organism dies, it is not absorbing any more CO2, and the amount of C14 that is in the body of the organism starts to decay according to the first order kinetics that we were talking about. And therefore, exploiting this fact, we can determine the age of, let's say, a piece of wood, which is, of course, a part of a dead organism, all right? And we're going to see some examples in lecture when we do problems involving radiocarbon dating. The only other thing I want to add here is that there are some limitations when it comes to radiocarbon dating. It only works for objects that are more than 50,000 years old, all right, in terms of accuracy. There are other forms of radiocarbon dating as well, but, well, not radiocarbon dating, but radioisotopic dating, but I won't get into that in this discussion, all right? The half-life of carbon-14 is shown here, 5,730 years, and this is what we use in order to carry out calculations in order to determine the age of artifacts and so on. All right. Okay, we're going to stop here, and I think I'm going to continue in the lecture with a discussion of nuclear transmutation and other topics. All right, so until next time.